Today's topic is Airbus fast and efficient prediction of fluid structure interactions using MSC Nastran aeroelasticity solutions. My name is Farnaz Jadbabi and I'm the Product Marketing Manager for MSC Nastran and Mark. I will be the host for this webinar. Today we have the pleasure of having Elisa Bosco from Airbus presenting for us, along with Fausto DiVincenzo from MSC Software. Before we get started, I would like you to kindly remind you to fill out our polling questions, as your feedback is greatly appreciated. At the end of this presentation, we will have 10 minutes for questions and answers. Please type your questions in the Q&A panel so we can address them all. And just wanted to let you know that a recording of this webinar will be uploaded and sent to you guys in a couple of days. At this point, I'm going to hand in the presentation to Elisa and Fausto. Thank you.
Thank you very much, Farnaz, for your introduction. So I will present in the next 40 minutes the activities that have been carried out in the frame of a PhD, a research program in between Airbus and the University HSA Toolkit in France, Toulouse. The main topic was the development of a method that allowed fast and efficient prediction of fluid structure interaction, and the method that has been developed is based on the MSC Nastran aeroelasticity solutions. So in the past few decades, the aircraft industry has seen a continuous growth in evolution, and amongst the many innovations, we have seen the use of more flexible wings and to enhance fuel efficiency, the use of bigger engine. The latter has caused the flaps and secondary structures at the flaps are fairing to be subjected to engine exhaust-induced excitation. It is therefore very important to account for the vibration generated in this way in the design process as early as the pre-design phase. And it is very important to be able to pinpoint the possible interaction in between inertial, elastic, and aerodynamic forces. The main point of the presentation are going to be an introduction on the problem that has motivated the study. I will also describe the wind tunnel testing activities carried out in the university to generate a database to validate the numerical method for fluid structure interaction that has been developed in the frame of this research project. Then I will also explain what has been the validation method and some conclusions. So the main objective, as I said, of the study was to develop a methodology that allowed the sizing of a structural component of choice and optimizing it with regards to vibration induced by the engine exhaust. It has been supposed that the possible mechanism of excitations that cause the vibration onto the structural component are mainly two. The first one is caused by an unsteady shear layer that develops because of the presence of zones with different velocities. Therefore, some vortexes will impact the structural component of interest at a certain frequency. Then the second mechanism is called here dynamic fluid structure interaction in between the jet and the component. Therefore, there's going to be an aerodynamic force that pushes the component away from its equilibrium position, and a structural repelling force that will take it back towards the equilibrium position. The two mechanisms of excitation will act at two different frequencies. In particular, the unsteady shear layer acts at a higher frequency and the dynamic fluid structure interaction at a lower frequency. So bearing in mind the objective, which was to develop a methodology for fine sizing of a structural component and optimizing it with regard to vibration induced by engine exhaust, and also considering what were the industrial constraints that we had, reducing the time of simulation as much as we could, and using software that are commonly available in the industrial environment, we have made some assumptions, some hypotheses to guide the research project itself. The first hypothesis that has been made was to target the low frequency excitation. So we are aiming at reproducing the dynamic flow structure interaction mechanism, and therefore the approach was a quasi-static approach, and it's been decided to consider that for our purposes only steady aerodynamics computation were necessary. In particular, this means that we have launched only Raynaud-Everest-Navier-Stokes computation using the software ELSA, which is commonly used in the industrial environment. Doing so, we have created a database of pressure around the structural component of interest by putting it at different relative positions with respect to the source of excitation, in this case the engine jet. And we have constructed this aerodynamic database of pressure that has been then used to recreate the current pressure distribution onto the structural component during the simulation of fluid structure interaction. The second hypothesis was to consider only small deformations. This meant that we have not considered deformation of the CFD mesh, and when launching the Raynaud's average Navier-Stokes computation, we have considered only rigid body motion of our structural component. Moreover, the only source of non-linearities is the mechanical friction. In particular, the mechanical friction in between the structural component and the rest of the structure through the attachment zones. So this assumption has allowed us to reintroduce the sources of non-linearities after the reduction process, because one of the industrial constraints, in fact, was to reduce the time of simulation, and therefore we have decided to draw upon reduced order models in both the aerodynamic and the structural model. During the time frame of the study, there was not a sufficient amount of data for validating the newly developed methodology with the industrial problem, which was in particular in this case a flapjack fairing excited by the engine exhaust. Therefore, we have decided to simplify the problem and use a plate mounted onto a wind tunnel test section so that it had just 1 degree of freedom that would reproduce a similar mechanism of interaction of the industrial problem. In this setup that I will describe very soon, we have been able to create a database of to validate the newly developed methodology. And once the methodology has been validated, we have been able to go back to the industrial problem and simulate the mechanism of interaction in between the flapjack fairing and the engine jet onto an Airbus aircraft. So let us now take a look to the wind tunnel testing activities. The objective was to reproduce, as I said, a similar mechanism of interaction in between the jet and the flapjack fairing in a wind tunnel. So we have a simplified problem, but that allowed us to run parametric studies because we had some variable characteristics of our system. Also, we have been able to monitor the critic zone and to see if instabilities due to aeroelastic phenomena would appear. And also, we have monitored the amplitude of the vibration of the operating structure. Data have been recorded in order to validate the numerical method. So the wind tunnel that we have used was a close return wind tunnel. The test section had a dimension of 0.7 by 0.45 meters, and the maximum speed obtained in the wind tunnel test section was of 35 meters per second. This wind tunnel has been customized by applying a wedge in the convergent wind tunnel section, in the wind tunnel convergent part. This wedge allowed us to divide the wind tunnel test session in two areas, one where the speed was higher and the other one where the speed was almost zero. In between these two areas, a shear layer has developed. If we take a look now more closely to the mechanical set, we have a single degree of freedom plate that is mounted on the wind tunnel test section floor, and we have some variable characteristic of this mechanical setup that allowed us to run a parametric study. In particular, we had 3 different plates with a variable height. Then on the closer to the trailing edge of this plate, there is an axis press fitted that is used to exert a repeating force onto the plate that is free to rotate around the axis that is fitted onto the leading edge. Also, the equilibrium position of the plate was variable, and it was possible to introduce non-linearities to the zones of attachment by applying a friction force that opposes to the rotation of the plate around its leading edge axis. So in order to reduce the time dedicated to the testing activities, we have decided to apply the Taguchi method. This method defines guidelines that allow to design the experiments in order to minimize the number of experiments given the complexity of the system. In our case, the complexities was given by 4 factors, which were the variable parameters of our mechanical system: the height of the plate, the stiffness at the trailing edge, the equilibrium position, and the wind tunnel speed in the test section. Then, for each of these factors, 3 levels, low, medium, and high, have been set. And given these complexities, it is possible to see that the minimum number of experiments to conduct is 9, where the combination of levels and factors are specified by the Taguchi method. And for each of these configurations, the experiments have been repeated 3 times in order to be able to measure the scatter of the results. The testing activities have been conducted on 2 levels. The first were some testing activity aiming at characterizing the equipment behavior, and in particular, we have characterized the behavior of the wind tunnel, so the flow in the wind tunnel test section, through particle image velocimetry, which is a flow measuring technique. And during these activities, the mechanical set was fixed at a fixed position in the wind tunnel test section. Then also the mechanical setup and the wind tunnel have been characterized in terms of structural dynamic behavior by running some impact testing. And as I said, 2 different impact testing have been done. The first one was with the full set, meaning the wind tunnel and the plate mechanical setup, and then only the plate with its axis has been characterized outside of the wind tunnel itself. Then the core of the testing activities was concerned the monitoring of the plate with the operating wind tunnel. And what we have done was to monitor the amplitude of the displacement, in particular amplitude of the rotation of the plate around the leading x-axis by using a laser displacement sensor that pointed at the trailing edge of the plate itself. Then we had an accelerometer that was fixed onto the trailing edge axis of the plate, some force transducer that monitored the force applied onto the springs at the trailing edge, and also at the spring that pushed a ring onto the test section floor in order to exert the friction force that opposes the movement of the plate. So after acquiring all the data, they have been post-processed, and in particular, it was very significant to show the main effect plot. The main effect plot shows the effect of the independent variable onto a dependent variable averaging over the other independent variable. For example, in these plots here, we can see the dependent variable frequency, first frequency of vibration of our mechanical system, and we can see what is the influence of the variation in the height of the plate, stiffness of the springs at the trailing edge of the plate, position of equilibrium of the plate with respect to the longitudinal axis of the wind tunnel test section, and also speed of the wind tunnel. And what can be seen is that no horizontal line appears, and this means that each of these independent variables have a main effect onto the dependent variables. In particular, it is possible to see how height and stiffness are the most influent independent variable onto the first frequency of vibration of the system. Then another dependent variable that we have looked at was the maximum displacement measured at the trailing edge of the plate. And here we can see that all of the factors, so all of the independent variables, have a very strong influence onto the displacement monitored at the trailing edge of the plate. Now, let us now take a look at the numerical method for fluid structure interaction that has been developed. And for that, I will let Fausto describe it in detail.
Okay, thank you, Elisa. And first of all, I would like to thank you and thank you, Airbus, for getting the time to do the webinar and for letting us share the activity that we have been working on for the last 3 years. And if you can go to the next slide, I can start talking about the software we have been employed for the activity. There were some technical challenges for these activities, because we had to select a solution able to take account for non-linearities, and for that reason we selected solution 400. And in terms of aerodynamic solver, we already said that we use the ELTA CFD code available in Toulouse, and we have even to thought about the interpolation between the CFD and the structural models, because as already explained by Elisa, in terms of the structure, we have used super elements, so we have to transfer a field of pressure to a bunch of grids. And in order to do it in a proper way, we use the spline interpolation available in MSC Nastran, that was spline 7. And we also employed the MSC Toolkit, that is a fly load pattern plugin that allows users to easily create spline between the aero and the structure. And on top of that, in order to couple Sol 400 with an external code, we employed Sol 400. And on the right side, you can have a look at the OpenFSI flowchart. And what we have, that as already explained by Elisa, we have a pressure database from which we get forces on the CFD wetted surface. These forces are then interpolated to the structure by means of the mesh mapping technology available in NASA and through the HSA Toolkit as well. And as soon as we have interpolated the forces on the structure, solve for and solve for the displacement, get the new position of the flap track fairing in this case, and send back to the aerodynamic tool developed by Airbus in the new position, and we get the new CFD pressure distribution on the wetted surface and so on. If we go to the next slide, we can have a look. We just wanted to spend a few words in terms of software and the OpenFSI. As some of you already used this solution, OpenFSI SCAD service provide a mechanism to exchange data between a software engine and an external code. And the important thing here to underline is that the external code can be whatever, can be a CFD solver, can be an Excel file, can be a lookup table, can be even another Nastran job. So we can couple Nastran to any external code. The important thing is that Nastran is weighting forces on structural nodes, define the wetted surface, and is going to send back displacement on the same structural nodes. So this means that if we want to couple software with an external CFD solver, and we have to take care even of the interpolation between CFD and the structural model. So this is the reason why we supported ELISA, and we developed an OpenFSI service in which we implemented the spline technology available in Nastran in order to exchange data between different discretization. Next slide, please. And in terms of pre-processing phase to create this spline matrix for the interpolation between the two models, we employ the HSA Toolkit that, as already said, is a plugin in flight loads, and it allows user to easily create a spline between the aero and the structural model. Meaning it creates several aero structure couples, and for each of these couple subdomains, it defines a spline 6 or a spline 7, depending on the user definition. And the important thing is that, as Elise is going to show you, we have to ensure that the load transfer from the CFD mesh to the structure will be conserved. And as you can see on the left side, on the bottom, that the structural monitor point and the aerodynamic monitor point reads the same values for the 3 components of forces and for the 3 moments. So that's what we wanted to achieve for this kind of simulation. In the next slide, I wanted just to speak about a little bit about the spline being used in this activity. Since we have just a bunch of external points that we had for the super elements, we had to transfer the load for a 3-dimensional wetted surface to these points, as you can see here with the yellow line connected together. This yellow line are just plot elements in order to see the deformation while post-tracking results. And we employ the spline 7, and the spline 7 algorithm creates a virtual beam, and all the aero and structural nodes are projected first onto this virtual beam, and RBF3 connection are created between this projection and the independent degrees of freedom that is the structure through, say, BASH, and the dependent aerodynamic grids are connecting to the projected nodes through rigid elements. As soon as the finite element model is created, Nastran solve for a static problem, transfer the load from the CFD to the structure, and if needed, gives us even the displacement of the aerodynamic model. As already said by Elisa, we didn't consider the deformation of the aerodynamic model, but only the alpha degrees that the structural components achieved during the simulation. Next slide, please. And here just a few words in terms of decoupling sequence. So we use a conventional serial staggered coupling. So this means that in explicit coupling, the CFD forces are sent to the structure at the beginning of each time step and displacement sent back at the end of the time step. As you can see on the right side, the pressure on the wet surface are calculated at each time step by giving the position of the flap track fairing calculated by Nastran. Through the spline mapping, the CFD pressure are interpolated on the structural model, and the software they calculate the new position that is sent back to the aero toolbox that calculates the new CFD pressure and send back this new load to the structural model. So the spline mapping is in between them, and all of this is software that OpenFSI customized service. And as you can see, here the aerodynamic toolbox is Python script based, so we can, as already said, we can couple software with any external solver, not only a CFD solver. So with this slide, I guess I end my presentation. So I will let Lisa continue through the presentation, and at the end we will be happy to reply to any question that you have. Thank you.
Thank you, Fausto. I will now go a little bit more into detail in what were the procedures applied to the structural and aerodynamic model. In particular, bearing in mind the fact that we needed to reduce as much as we could the time of simulations of the fluid structure interaction simulation themselves, we have been using a reduced order model. In particular, for what concerns the finite element model, we have applied the technique of component mode synthesis that allows to represent the behavior of the entire structure starting from its component. In particular, so the structure is divided into substructures that are combined to form the complete system. In this process, it is very important to pinpoint what are the nodes that we are using for load transfer and what are the nodes that we want to monitor for displacement, speeds, and acceleration monitoring, and also what are the elements for stress monitoring, because those elements will be extracted from the model and then reintroduced after the reduction process. As an example, we have the example of the flap track fairing here, in which we started from a very detailed model of the flap track fairing itself, and we have reduced it to a total amount of 19 elements, 19 nodes. And here it is possible to see the shape of the flap track fairing. The loads were transferred only on the external skin of the fairing itself, and then we had some elements also to monitor stresses. And then in the case of the plate and beam model for the mechanical setup of the wind tunnel itself, we have reduced also the number of elements and nodes from 319 to 17. In order to check that the reduced order models behave exactly as the original model, we have applied the technique of the model assurance criterion in order to check the coherence in between the modes of the two models. So we have used a nonlinear solver, and in general, in a nonlinear relation, the stiffness matrix depends on the applied forces and onto the displacements of the nodes. But in our case, we are also considering reduced order models for which the stiffness matrix is a constant. But one of the hypotheses of our study was that the main sources of nonlinearities were mechanical friction in the zones of the attachment in between the component and the rest of the structure. Therefore, we have been able to apply the reduction of our system and then reintroduce the residual elements of interest and the nonlinear relationship in the attachment in between the structural component and the rest of the structure. In particular, we have considered in various steps of our studies C-gap elements to represent the connection, for example, in between the flat jack fairings and the rest of the structure, or contact forces, or nonlinear springs, for example, in the case of the wind tunnel testing activities, in order to represent the behavior of the springs at the attachment of the trailing edge axis of the plate itself. So let us now take a look to the way we have constructed the aerodynamic database. The first thing, it is very important for us to observe or the system of interest and define what are the active variables of our system. In the case, for example, of the plate in the wind tunnel, we had just 1 degree of freedom, which was the rotation of the plate around its leading edge axis, and that was the degree of freedom active during the creation of the aerodynamic database. And therefore, what we have done was considering different relative positions of the plate with respect to the source of excitation, so running Reynolds average Navier-Stokes computations to create a database of pressure. The numerical simulation that have been considered were both Reynolds average Navier-Stokes computation and large ID simulation with an LBM software Palabos, and the results have been compared. Then the reduction process has been applied also to the aerodynamic database, and we have decided to use the technique of proper orthogonal decomposition that allowed us to obtain a low dimension approximate description of the initial higher dimensional process. In the case, for example, of a simple degree of freedom system, this translates into applying a singular value decomposition, and in order to reduce the dimension of the database, some energetic considerations have been applied. In particular, it is possible to observe that most of the energetic content of the flow is contained in the very first singular values, and the system has been cropped accordingly. So now let us take a look to the way the fluid structure interaction method that has been developed has been validated. So first, we have compared the numerical results of 2 models. A model that is based on ELSA, that has been used to run unsteady Reynolds average computation, then average in time to obtain a steady representation of the flow, and also an LES LPM Palabos. And these, the results of these computations have been compared to what has been acquired to particle image velocimetry. So in this slide, it is possible to compare the velocity field in the wind tunnel test section in the case of particle image velocimetry, Uran's average Navier-Stokes computations, and then LES LPM. It is possible to see that there is a different representation in particular of the shear layer, and the main difference in between the three representation of the flow is the way the flow is distributed within the left and the right hand side of the plate itself. If we fix the position in the longitudinal axis of the wind tunnel test section, we can compare also the speed profile, and it is possible to see that in particular the trends shown by the three flow fields are showing a good accordance. In fact, at the end of our study, the choice in between Uran's average computation and LBM has been based mainly in the time of simulation necessary for representing the flow field, and the amount of hours was a lot less in the case of Uran's average computations. So that's the method that has been finally used to create the pressure database. In a similar manner, also the structural model has been validated. In this case, we are considering a plate with the axis at the leading edge and the trailing edge, and it has been validated through comparison with the results and experimental model analysis. In this case, we used the technique of the impact testing, rolling hammer. We have used just one triaxial accelerometer, and here in this configuration, the plate was clamped on a test bench, and the same boundary condition to match the testing configuration have been reproduced in our finite element model. And it is possible to see how the frequency of vibration of the plates are well represented, especially in the low frequency band, which is the frequency bandwidth of interest of our study, because again, one of the hypotheses that we had made for the development of this method was to aim at representing the low frequency fluid structure dynamic interaction in between the structural component and the source of excitation. So let us now take a look to the results of the simulations, fluid structure interaction simulation, and compare them with the testing activities in terms of frequency. Here again, we are looking at the first frequency of vibration of our mechanical system, and it's possible to see how we are finding a very good match in between the wind tunnel testing results, which can be seen here in blue, and the fluid structure interaction simulations. Here we are considering three different values for the springs at the trailing edge of the plate itself. Then the other comparison that has been made was to see to look at the maximum displacement of a point located at the trailing edge of the plate in the wind tunnel. In this case, we have considered non-linear springs for representing the springs at the trailing edge. And what can be seen is that at this stage, we are able to predict the order of magnitude of the displacement itself. And it was a very promising result because the number of complexities considered in the finite element model was very limited, in the sense that we have considered only the nonlinear springs as source of nonlinearities in this case. So I will now wrap up this discussion, making some conclusions, the conclusion that we have made at the end of this 3-year long research project. which are that we have been able, through the collaboration in between the lab at ESA, Supero, Airbus, and MSC, to develop a new tool that can simulate fluid structure interaction, taking into account the non-linearities that are present in the attachment zone in between the component considered and the rest of the structure. This tool can be integrated in the industrial design process because it is based on software that are commonly available in the industrial environment itself. So the strategic choices that have been made was to use reduced order models in order to reduce the time of simulation, and to use again software that are commonly employed in the industry. The method is used to reproduce transient response analysis because we have considered structural components that are subjected to time-varying excitation, as for example, time-varying excitation due to the engine jet. The test campaign has been designed in order to collect a sufficient amount of data that would allow us to validate the newly developed methodology. And also, the testing campaign has allowed us to run a parametric study and better understand which were the most important parameters that played a game in the interaction between a structural component and the engine jet. And the data has been used for validating the fluid structure interaction method. The wind tunnel testing activities have allowed us to understand that the frequency of vibration is at low frequency of the mechanical system was predominantly set by the structural characteristics of the system, and there is no interference in between the characteristic frequency of our shear layer and the low frequency behavior of the plates. Also, no divergent behavior has been identified, but only a sustained vibration that is in line effectively with the behavior observed on the flat track fairing itself. So the tool for fluid structure interaction that has been developed has shown to be adaptable and efficient. It has been applied to reproduce the wind tunnel test configuration, and we have obtained a good simulation of the fluid flow and of the mechanical set, and also a good prediction of the first frequency of vibration of the mechanical set itself. The correct estimation of the displacement of the structure has been obtained, but it is possible to better the prediction of the displacement by adding further complexities to our mechanical system. The same method is being also applied to the flat track fairing of an Airbus aircraft, and also again we have obtained a good estimation of the first frequency of vibration of the flat track fairing itself by applying this method. So in terms of the perspective, now my PhD is ended, but some more research projects will effectively be developed starting from the achievements of this first 3 years on working on this project. And the aim is going to be to push forward the non-linearities modeling in order to better the prediction of the displacement, and to validate further the method using also the data collected in the dissipative configuration of the system. In order to enhance the efficiencies in terms of time of simulation, a further step could be to parallelize the fluid structure interaction code and to validate the method also in its industrial application. So one of the suggestions that we have made after the study was that a fatigue analysis of the components subject to this type of aerodynamic excitation is recommended, and also one of the main goals would be to apply this method to other fluid structure interaction problems. So I thank you very much for the attention, for having attended also this webinar, and I would like also to thank MSC for giving us the chance to show what we have been working on for 3 years during this PhD, and for the good collaboration that we had. And I will now let you sometimes to ask any question that you would like to ask. Thank you very much.